Hello there. This lecture is all about understanding the mean and the weighted mean. So the mean is really just the same thing as saying the average, and there's multiple different ways to calculate the mean depending on the nature of the data that you're given. So we're going to start off by looking at just the basic way to calculate a mean when you have raw data, and then we're going to get into some more complicated situations where you have limited information or information presented in a slightly different way, and you still want to calculate an accurate mean. So you've heard me say the word calculate a couple times. So this is the first lecture. We are actually going to need to get out a calculator and work through some computations. I'm going to show you how to do the computations in the lecture, and then for the lecture quiz questions at the end, you will be doing some math. Granted, I'm going to try to keep it basic, and I'm going to show you even more things that you can do with your Excel practice assignment.
So as I mentioned earlier, the mean is just the average or the arithmetic average. And it basically just gives you a single value that tells you the general trend in scores in your data. So up to this point, we've been looking at tables and figures and graphs and trying to, make sense of data. But now we're moving on to focusing on numeric values that can tell you the trends in the data instead of displays. So the mean is probably the most commonly used, and it's nice because it includes every single score in the data set in the computation. But the mean can be problematic if you don't have a normal distribution. If you're working with data that's highly skewed, that mean is going to be biased. So for instance, if you're looking at income among NSC employees, the president's income is so high that it's going to bias the mean towards it, and it's going to make it look like overall we're making more money than we really are because there's a few people who make quite a bit of money. Here's the formulas that you'll be using to calculate the mean, and you'll see that basically they're the same. One of them is for a population and one of them is for a sample. So as a refresher, a population is if you measure every single person or thing that you're interested in, and then a sample is a subset of that population that you draw to try to represent that population. So if you look at the population mean, you'll see that it's symbolized as a mu. That's what that's called, the Greek letter. And then this sum of x is just you add all the scores together. So add all scores together. And then you'll see there's an n at the bottom, and that is the total number of scores in the population, or the population size. Total number of scores. Okay? Now, when it comes to the sample mean, you'll see that that symbol is x bar, but it is calculated essentially the same way. This sum of x is still adding all the scores together, and this n is now the sample size instead of the population size, but it still represents the total number of scores. So the sampling error is really getting at the naturally occurring difference between a population mean and a sample mean. Naturally occurring, random, chance. Just due to chance, any sample that you take from the population is going to have some error associated with it in terms of how well it represents the population. So if you think about that concept, let's think about salary again among NSC employees. Let's say that I know the mean salary of all NSC employees. And let's say I take a sample of 50 NSC employees, just randomly plucking them from a list. Chances are, even though I did random selection, which is supposed to be pretty accurate, and it's a relatively large sample, there's going to be a difference between that sample mean salary and the population mean just due to random chance. Now, if I took a larger sample of like 150 employees, I would be more confident that that sample would be a better representation of the population. And mathematically, it would probably work out that the mean for that larger sample of 150 would be closer to the population mean than the mean from that smaller sample of just 50. So now we're going to look at a very basic example of computing the mean, looking at two different tellers at Chase Bank on Green Valley Parkway. And you'll see that there's 10 transactions in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our sample size is going to be 10. And then we're going to add up all these scores to get the total number of seconds spent on transactions among 10 transactions. Then you'll see we're going to do the same thing for Bob here. So here you will see those formulas, and I use the sample version of the formula because we are only looking at 10 transactions, and chances are they had more than that in any given day or in their career in general. So you'll see that if we add up all these values, the sum of X is 990. So among all those 10 transactions, Maria spent 990 seconds with her customers. And you'll see that reflected right here in the numerator. That's your sum of X. Then we don't want just the sum. We don't want to know in total how many minutes she spent or how many seconds she spent. We want to know the average. So you take that 990, you divide it by the fact that we have 10 transactions here, and you get a mean of 99. So on average, Maria spent 99 seconds with her customers. Now let's look at Bob. We add up all of those scores across those 10 transactions to get that sum of X of 870. So across all those 10 transactions, he spent 870 seconds with his customers. So we take that sum of X, 870, divide it by the fact that we have 10 transactions, our sample size, and you end up with 87. So on average, Bob spent 87 seconds per transaction with customers. And if we compare those two values, you can see that Maria, on average, spent a little more time with her customers than Bob did. So now let's take a look at the weighted mean. And there's slightly different formulas here than you see in your textbook. I tried to simplify it for you a bit, so just keep that in mind. And you'll also notice here, and we'll get into in a minute, but really there's the same rationale for the formula when you use the frequency distribution and for a frequency or for the formula when you don't have raw data. Same rationale there, but a slightly different approach to make it a little simpler for you. So the weighted mean is symbolized for a population as a mu with a W subscript, or the X bar if you're using a sample with a W subscript. And you'll see that consistent for either way you're doing it. So I'll show you examples of this in practice, but first I want to explain the formulas. So the numerator here is taking the sum of X times F. If you think about it and you're using a frequency distribution table where you have X column and F column, if you just add up these X values, you're going to miss out on the fact that some of these values occur more frequently than others, right? So you're not taking the frequency into account. So what you would have to do to use this formula is take each X, multiply it by F, and then you'll add those values together to get your numerator. Then, to get your denominator, that's the total frequency or the total sampler population size, and you would just add these values together to get your sample size. All right, so remember, X times F, and then add together. You can't just add the X column when you're working with frequency distribution tables because there's multiple of each score in your data set. Now let's take a look at the second table here. This is when you're not using raw data, and oftentimes you're going to be using means and sample sizes and kind of combining those samples to come up with an overall mean. So these two formulas are completely equivalent. And the reason that is, and I can prove it with algebra, is that the formula for the mean is the sum of X divided by the sample size. So if I don't give you the mean, right? If I don't give you the sum of X here, you can figure out what it is by taking this formula. You multiply n by both sides, and the mean times the sample size gives you the sum of X. So that's why these two formulas are completely equivalent, because the sum of X is the same as taking the mean times the sample size. Then you'll see the denominator is the exact same sample size as here. Now, you'll see that this is kind of spelled out in words. It's the total of all values, the sum of X for all different groups while taking the sample sizes into account, divided by the total number of items that you're looking at or people that you're looking at. Now you see this little k here? That just means that this formula can go on forever. If you had 4 groups, you would have mean 1 times n1 plus mean 2 times n2 plus mean 3 times n3 plus mean 4 times n4, and then the denominator you'd have n1 plus n2 plus n3 plus n4. So it can just go on forever, however many groups that you are trying to combine to get a weighted mean for. So now let's take a look at an actual example of using a frequency distribution table to compute a weighted mean. So in this example, Haley opened an Etsy shop 200 days ago to sell her trendy handmade clothing and accessories for kids and adults. She's been tracking the number of sales in the table and graph below. Here's your frequency distribution table. Here's your graph. But she wants to know the total number and mean number of sales since opening. Now you'll notice this says 200 days. So if you add these together, you're going to get 200, and that is the size of your population or sample right there. So looking at this table and graph, we don't automatically know the total number of sales or the mean number. So in the next slide, I'm going to show you how you'll compute that. So now you can see the formula that we're going to be using and just the table for the data. So remember, Haley wants to know the total number and the weighted mean number of sales since opening. So to get the total number of sales, we can't just say, okay, total number of items sold, 0 plus 1 plus 2 plus 3 plus 4, 5. Can't do that, remember? You have to take the frequency into account. And remember, whenever you see data presented to you, because you're going to see these notations, you need to identify what is X and what is F. X represents the actual values that you're measuring, the variable of interest, which in this case is the number of items sold, right? So you can't just add that up to get the total number of items because you have to take the frequencies, the number of times those values appear in your data set, into account. And again, just to reiterate, you'll see that the sum of the frequencies is 200 because she's looking at a data set that consists of 200 days. So let's figure out how many total items Haley sold in this 200-day period. So you take each X value times each F value, and then you add those values together. So you'll see 0 times 16 and 1 times 20 and 2 times 35, just all the way across, all the way down. Then you add these values together, and you find that in the last 200 days, since she opened her Etsy shop, Haley has sold 657 items. But that's not all, right? She wanted to also know the mean, or in this case, the weighted mean of how many items she sold. So we've got both the values we need, right? We've got the sum of X times F, or the total number of sales, and that is 657. We also know how many days, or the sum of the frequencies, or the population size in this case, since that's all the days she's been open, is equal to 200. And 657 total sales divided by the total days she's been open gives you 3.285 sales per day on average. It's all squeaky. So check this out. Let's see if this makes sense. And let's make that very much look like a period and not a comma. Whenever you do some math, you need to go back and look at your data to make sure it makes sense. If I got something that was like 7, 8, 9, I wouldn't be feeling good about that because the majority of my scores are falling right here between the 2s and the 4s. See that? So because the majority of my scores are between 2s and 4s and I ended up with something right in the middle of that, I'm feeling pretty good about my computation for the mean. This mean makes sense based on the nature of my data. And now you can see how it's kind of a handy explanation without looking at all these values. Now let's take a look at an example where we don't have the raw data. We don't necessarily know the raw scores and the frequencies associated with them, but now we have sample means and sample sizes that we want to combine to have an accurate overall weighted mean for the entire data set. So this data represents mean medical payments and number of employees from 5 Nike plants in China. So we want to know what is the total number of employees, the total amount of medical payments, and the overall weighted mean medical payment per employee for these 5 plants. So here you see both versions of that weighted mean formula without raw data. If I gave you the sum of X for each group, you could just use this first version, but I did not. You have to take the mean and multiply it by the sample size to get the sum of X for each group. So if we look at this, this is basically what we're doing here. So we take the mean of 7,400, multiply it by the 123 employees, and in plant 1, they spent $910,200 on medical payments. You see the same thing for the next plant. You take the number or the mean medical payment per employee, multiply it by the number of employees, and in this plant, plant 2, they spent $5,788,800 on medical payments. Now, that doesn't necessarily mean that their employees were hurt more, even though you can tell by the mean that they were. They also, this number is much larger because this is a much larger sample. So you see that we do that consistently across the board. Take that mean, multiply it by the sample size, and then you end up with the total amount paid across all plants. Is $10,731,300. So that answers this question right here, right? The total amount of medical payments. And then we want to make that into an average by dividing by the total number of employees, 957, answering that first question here. So out of all these 957 employees, a total of $10,731,300 was paid for medical across all plants. But we want to know the weighted mean, or the average. So our weighted mean equals the sum of, you're adding all these together, x times n right across the board. So the total number of, or the total value of medical payments, $10,731,300 divided by the total number of employees, 957, and you end up with a weighted mean of $11,213. I'm going to round to the hundreds place since we're dealing with money, 48 cents. Now let's see if that makes sense. And let's take a look. So $11,213, 48 cents. Well, that's a lot higher than this one, but it's pretty darn close to this one. It's higher than this one and this one. But if you think about it, those lower numbers are coming from smaller samples. So this really large sample of 402 is going to drive that weighted mean upwards. And then it's kind of resting right here in the middle. So I'm feeling like this is a pretty darn good number. I'm not suspicious about it. If I got something crazy, if I did some math wrong and I got a weird number, you'd be able to tell by comparing your weighted mean to the means overall. And typically, your weighted mean is going to be closer to the means from the larger sample sizes. And we see that reflected right here. So I'm feeling pretty confident about my weighted mean. So now let's take a look at an example where you're computing the weighted mean without raw data, but the data is not provided in a table for you. So don't get spoiled by having data always beautiful in a table to do your math. Be ready to do math and sometimes with paragraph form numbers. So let's take a look at this. So let's say I've been teaching Econ 261 online for 3 semesters. And each semester I had a different number of students and a different mean grade. But I want to know the overall final mean grade for all classes combined. That requires a weighted mean. I can't simply add these 3 values together and divide by 3 to get a mean, because that's not taking into account that I have a different number of students each semester. Now, if I had 30 students each semester, I could do that, but that's not the case, so we have to do the weighted mean. Now, this is another situation where I don't give you the sum of x. I don't tell you the total grade. You have to figure that out by taking the mean and multiplying it by the sample size. So let's do this. To get our weighted mean, we're going to have, 79.5 was the mean for the first semester, multiplied by the sample size for the first semester, which is 25, plus the mean grade for the second semester, 82.5, times 28 students, plus the mean grade for the third semester, 84.5, times multiplied by those 30 students. And then we're going to divide that by all my sample sizes added together. So 25 plus 28 plus 30. So I'm going to solve for my multiplication first. So 79.5 times 25 is 1,987.5 plus 82.5 times 28, 2,310 plus 84.5 times 30, which is 2,535. And then we're going to divide that by 25 plus 28 plus 30, which is 83. Then you end up with, you got to add all those values in the numerator together, 6,832.5 divided by that 83. So if we look here, if I added up all of the grades for all of my students, we would have 6,832.5 divided by the total number of students, and we get an average grade of 82.319. That's our final answer. So on average, over the past 3 semesters, students have achieved an average grade of an 82.319. So now let's take a look at a different example for weighted means when you have weighted evaluations. So sometimes performance appraisal scores are, based on different categories, and some categories are more important or more relevant to the job than others, so they're weighted more heavily in their final evaluation. Sometimes you'll have a professor or a teacher that's going to, instead of grading you based on a point structure, they're going to have different assignment categories that are worth a certain percentage of your grade, and then you have to tabulate what your final grade is based on the percentage you got in that category multiplied by how much that category was actually worth in terms of your final grade. So here's an example of a kind of performance-based weighted mean evaluation. So prospective employees for HR management job must complete a battery of selection tests with a final score of 80% or above to be considered for hire. So employees are coming in, they are being judged in these different ways. So although each test is job related, a couple tests are thought to be more predictive of performance than others and are thus given more weight in the final score. So that table below represents John's scores on each selection test. So they gave them a mock performance appraisal to do. They gave them a quiz on employment law. They asked them questions about how to perform a job analysis, and then they gave them a math skills exam. Now, based on these weights that you see here, you can tell that this company doesn't want to get sued, right? They're pretty concerned about employment law because that is the most heavily weighted test that they give. And math skills are probably the least important to them, probably because they have a software program that can help the HR managers do the job. So you'll see here are the different weights, and then here's the actual performance for each category for this particular prospective employee. So now you can see the math behind this, right? We're taking each weight, and I just means for that particular category, multiply it by the actual grade, and then we're dividing by the sum of the weights. Now be careful. Notice that once you start to do the math, you turn the weight into a decimal. So I'll put a little note. Convert the weight into a decimal. And to do that, you just take the percentage, divide it by 100. Or you can just scoot the decimal place or the decimal 2 places to the left. So you take that weight that is now a decimal, make sure that you add them up, you get a sum of 1 because that's 100% of the evaluation. You have 0.20 times 70, you don't change that into a decimal, you keep it 70, you get 14. 0.40 times 100, 40. 0.25 times 70, 17.5, and 0.15 times 60 is 9. These get added up, and you end up with 80.5% final grade. So in this case, John would definitely be considered for hire. His final weighted score is greater than 80%, and that's what we wanted to have up here because it's an 80.5%.